Alright, gang, here we go. This is for physics, Unit 8, Part 4. We're talking about light and color. Should be fun. Alright, so let's think about color for a second. So if you're looking at a leaf, it appears green, and the reason it appears green is because light comes in, hits it, and you see it. Wow! No, but really though, you know that if you put light through a prism, or if you've seen a rainbow, that white light is made up of a bunch of different colors, specifically these six: red, orange, yellow, green, blue, and violet. Alright, whatever color you see is because the substance you're looking at absorbed all of the colors of the rainbow except for the color that you're seeing. So you see a leaf is green because it absorbed red, orange, yellow, blue, and violet. Okay, and the green bounced off, and that's what your eye sees because that's what was left. Okay, parts of the U.S. flag appear red because it absorbed orange, yellow, green, blue, and violet and left the red behind. All right, so anything that you see it that's a specific color is because they absorb specific parts of the rainbow. Okay, and so it can absorb different ranges within those as well. All right, so it doesn't necessarily need to be one of those six colors. It can be a mix of the two, and that's where we get the different shades of those colors. All right, so any color that's not absorbed has to have been reflected by that light. So that's essentially why you see different colors, and that makes sense, right? So if a light comes in and it gets mixed, then we get this thing called color addition. Okay, color addition is the mix of all the colors of the spectrum. Okay, so white light is the color addition or the mixture of all of the colors, and we get white when we mix all these six colors together. All right, and so we divide these guys into what are called primary colors, primary additive colors, and then complementary additive colors. Okay, primary additive colors are thus red, green, and blue. All right, red, green, and blue are the primary additive colors. Remember that additive part because in a second we'll talk about subtractive colors, and they're different, okay, but they're still primary colors. All right, but specifically the primary additive colors, remember they add to make white, okay, and so these are red, green, and blue. All right. And so addition of these colors with other and of these three with intensities make all the different colors. So if you ever mixed with Photoshop or anything Photoshop or like with the color settings on a monitor or a TV, something like that, it's always based on RGB values. You've probably heard that before, RGB values. Those RGB values are red, green, and blue. They're the primary additive colors. And so your TV or your computer monitor or your phone are producing different colors because they've got like these little tiny pixels in them, and these little pixels are really close together, and they all show either red, green, or blue, and then the computer controls the intensity of the light that's produced by the red, green, or blue. So if it wants to show you red, then it makes the red one shine at 100% intensity and makes the green and blue at 0. If I want to show green, green would be 100, red and blue would be 0. And then any mix would be some variation of the intensities of those two, of all three of them or just two of them, just depending on what color it needs to show. All right, so here's your primary colors. All right, so here's your red down here, and then your green, and then your blue. All right, notice that when we mix all three of them together, we get white. All right, so here's our white, and so this color addition, red, green, and blue make white. So, but we can also form these complementary colors. So if red and green mix, we get yellow. All right, if blue and green mix, we get cyan. All right, that's what color that's called. And then if red and blue mix here, we get magenta. All right, if we mix any of these two guys that are across from one another, then we'll always get white light. And so that's how we define what the complementary colors are. All right, so blue's complementary color is yellow because if we mix blue and yellow light together, we should get white. All right, if we mix magenta and green together, we'll get white. Those are complementary, so magenta's green's complementary color. And if we mix cyan with red, then we'll get white light. All right, so those are your complementary colors: magenta, cyan, and yellow, respectively. All right. Now, the subtractive colors are formed because of pigments. All right. All right, so if you take a red and blue crayon and mix them, you get green, not white. You understand that. So this is different, and this is because pigments, or like wax or paint, rely on colors of light that are absorbed or subtracted from the incoming light. So it works opposite, whereas the additive colors were based off the fact that the things that we see are based off of what we see, or is based off what was not absorbed. Pigments work opposite. They're based off what we can't see or what was subtracted subtracted from light. And so you get the opposite. So essentially what happens is in the subtractive primary colors, your colors chart gets mixed or gets flipped. Okay, so the things that were complementary are now primary. All right, so the complementary color here, it might look like blue, but this is actually cyan. Okay, and this guy's yellow. Okay, and then this last one, if you're paying attention, would be our magenta. All right, and then we can mix these two together. So a cyan and a magenta will give us blue. All right, a cyan and a red will get us, or sorry, I'm doing it backwards. Cyan and magenta get us blue. Cyan and yellow give us green. All right, and then yellow and magenta give us red. And then if we mix, and then we can also do the complementary trick again. Oops, if we do the complementary trick again, we can see that a cyan color, all right, mixed with this red will give us black. All right, and so there, and it's black because it's absorbed all of the colors. Okay, as opposed to all of the colors not being absorbed in white light. All right, so, and it's black because then there's no light left. All right. Okay, so polarized light. So that's really all I want you to know for color. Okay, polarized light. Now this is super interesting. Okay, if you think about light that's coming in, we know that a light is oscillating electric and magnetic fields, right? So it's like this, and then your magnetic fields would do something like this. All right. So we could draw like a little lines here to help us picture, or maybe we couldn't. So here's the electric line, and here is the magnetic field lines. And so here's, see, now I've lost track. These are our up and downs, and these are our back and forths, right? And then, see, I did that one backwards, didn't I? Shoot, dang. All right, we'll just erase that one and pretend it didn't happen. Oh, no. All right, well, whatever. We've ruined it now. Okay, so, but what occurs is we have polarization occurring, all right, and we have oscillating electric and magnetic fields. These three are pretty good, so we're just going to run with those three, okay, and the electric field will go up and down, and remember the magnetic field is perpendicular to that, so it would go in and out and up and down, whatever else, okay, and so if we're unpolarized, this means that if our light is traveling one direction, our electric fields could be pointed in any direction, right, so so in this case here, so we can imagine if the light is coming out at us, okay, so imagine this is the point of the light that's coming out at you, okay, and we just drew the path of the electric field. This electric field would be going up and down. Now, there's nothing to say, if it's coming out at you, there's nothing to say that your electric field couldn't also be coming like this, or like this, or like this, or any version of this at 90 degrees, right? And so we get this unpolarized light, is this light that's just randomly whatever direction it happens to be. It doesn't really matter. But we can polarize that light by passing it through something, or, we'll talk about different factors that create polarized light here in a little bit. But essentially when we get polarized light is we reduce the amount of light so that only the light can be facing the same direction. So notice this is polarized light. Notice that these electric fields here are always pointing up and down. These lighter green ones are the electric fields. Notice that they're always pointing up and down. The magnetic field is always going in and out 90 degrees to that. Whereas up here in our unpolarized light, these electric fields are pointing in lots of different directions. All right, so essentially what happens is unpolarized light consists of light with electric and magnetic fields vibrating in all directions. So that's unpolarized light. And polarized light have fields vibrating in only one direction. All right, so in this case, the electric field is vertically polarized. So we can send our light through polarizers, which essentially block out the light except for what we want to see. So here's unpolarized light, so the sun coming in, and this light is coming in and it's facing any direction it wants. Then it hits a polarizer, and based on the transmission axis, that's this line that determines what angle of light is going to go through. And so we have this light coming through, and then it gets turned or blocked so that only this polarized light can come through, and then you can also send it through this other guy here to polarize it again so it gets turned even more. All right, so polarizing filters only allow light with a specific electric field aligned with the transmission axis to pass through. So we could imagine if we have sunglasses here, right? So here's a pair of sunglasses, okay? And so you could imagine, like, we could have our sunglasses, and so you've probably heard of polarized sunglasses, right? And so essentially in polarized sunglasses, you have little tiny gaps in between your things here. And so just imagine for a second if you have a colander, right, for cooking spaghetti, for drying them out, and you wanted to pass through dry spaghetti through your colander, the only dry spaghetti that would make it through your colander is the ones that were aligned directly with your holes, that would go up and down with your holes. If they came in flat, they wouldn't pass through those holes. So the same idea here with a polarizing filter is that it'll only allow the light through that matches up with those holes. If your light that's coming in is vibrating perpendicular to these lines like this, as it hits your sunglasses, it's not going to make it through. It gets blocked. Now, but if your light matches up and it kind of does this number as it comes in, okay, it will fit through those holes, right? And it'll make it through your sunglasses. And so that's essentially how polarizing sunglasses work, is it's going to block the light. A couple years ago now, we had the solar eclipse that was a big deal around here, and we put on these special glasses. Then essentially these two glasses were two polarizing filters that were on top of one another, and it blocked 99% of the light that came through. And that's really all it did, was just block a bunch of light so you could look directly at the sun. All right. Now, there are several times when naturally polarized light occurs, and one of these things is when unpolarized light hits some sort of reflecting surface. So like the surface of a lake, or water that's on your that's water on the pavement, or so on and so forth. Or like if you're into fishing. Okay, so like you're out, they'll show you like, oh, this, these are special sunglasses that allow you to see the fish under the water, or something like that. And so essentially what's occurring with this is unpolarized light comes in like so, comes in, bounce, hits the surface of the water, and then bounces off again. Now, because this is unpolarized light, they only show it bouncing one direction, but really it could be in any direction. It could be in and out of the page, or it could be any of these angles. And it comes in, when it reflects off the surface, it automatically gets polarized so that it lines up with the transmission axis of the water. So it's going to be parallel. So all of this light that bounces off this water is going to be, the electric field is going to be coming in and out of the page, and it's traveling in the same direction up here, right? The light came here and then bounced up this way, but the transmission, or these electric fields, are going to be lined up so they're parallel with this water down here, and then so on and so forth. And so then they ask us, is like, well, where should our transmission axis be on our polarization in order to block out this specific light? We don't want to block out all light, because we still like to be able to see, but specifically if we want to reduce the glare off this water, we would want to block out the light that's traveling and has its transmission axis, or the electric field vibrating in and out of the page. So the best way to do it is if we look at the lenses. So this is the lens of our sunglasses. If we designed our sunglass like this, then any light that came into the page, right, any light that came in like that was parallel to the ground, it would automatically get blocked, because it can't make it through those transmission axis. Okay, and so fishermen like him because it's blocked off those glare, that sun glare, off the surface of the water, and so you can see the light that bounced off the fish instead of the light that bounced off the surface of the water. Now, naturally polarized lights, okay, another example is when light passes through different parts of the atmosphere, especially if it changes density. Like if light goes through a cloud, it gets polarized as it passes through. Okay, so light getting scattered off of a cloud gets polarized based off the molecules that are in the cloud, specifically water. Okay, so it hits those water, and those water molecules are made out of atoms and electrons. Those electrons absorb that energy and then get excited, and then they get released, and when they get released, they release that energy again. Or when they get unexcited, they release that energy, and the energy goes out, and that energy, or that light, is again polarized. And it's all because of the way the waters are and the way the electrons fall. It becomes polarized as it comes out again. And so photographers use this trick. If you've ever tried to take a picture of a cloud with just your phone, or with just a dollar camera or something like that, you'll notice that it never looks quite as good as you'd expect it to be. But the trick is, photographers will use what are called polarizing filters, and these will just be filters that go on the end of your cameras, and they'll be able to turn the polarizing filter so it only blocks out all of the light except for the light that's in that specific polarization based off it coming off the cloud. So it makes the blue sky much darker, and it makes the clouds seem like they're standing out more. So that's how that works. And that's it for part 4. So we talked about light and color, primary additive colors, primary subtractive colors, and polarization. A couple of different things just to wrap up this next part here. Let me know if you have any questions, and I'll see you on the flip side.